PCIe is an abbreviation for Peripheral Component Interconnect Express, an electrical interface standard used to connect high-speed add-in printed circuit boards to computer motherboards, GPUs, RAID cards, and SSD cards, and all kinds of add-in cards. PCIe are found in many sizes. It could be X1, X4, X8, X16, or even X32. X1 stands for 1 TX differential line and 1 RX differential line. So X32 will have 32 TX differential lines and 32 RX differential lines. You can use Ansys tool to design a motherboard or an add-in board. You can use SI Wave, HFSS, or 3D layout. Now, if your board contains PCIe lines, how do you know your design is correct? You need to check it against the PCIe specifications. So we build, assemble, and test the PCB using well-known equipment, but this is a costly way. You would like to know if your design is acceptable while designing the PCB. You can use the PCIe template that Ozen Engineering developed to do that, the one you see here. The template supports from PCIe 1 to PCIe 7 standards. If you open any one of them, you will find many circuits. Some of these have more than one circuit. All the necessary constraints, specifications, and limits are embedded in these circuits. We're talking about hundreds of numbers embedded in all these circuits. As we will see, these numbers are scattered in many places, but they are where they are supposed to be. Start first by obtaining the S parameters for your PCB, whether it's simulated or measured. Back to our template. What will you find in each circuit? So if I open any one of these circuits, this is what you're gonna see. The first thing you will notice is the information below the circuit. The first part is a detailed description of how to use the circuit. The second one is some of the standards used in the circuit. Third is what we call the preset setup for each standard to be used in the circuit. We will talk more about it later on. The fourth is a list of circuit's local variables and their descriptions. These are the local variables used in the circuit, and changing them will only change the circuit. There are global variables. You will see them if you click on the name of the standard here. If you change these ones, it will change all the circuits in the standard, all of these circuits here. All of these circuits, because it's common to all of them. At the bottom, you will find examples of the results. These are just pictures to demonstrate how the results should look like. This is in case one of the graphs changes, then the user can change it back to how it should look like. So we have this one for the bathtub, and we have this one for the eye height measurements. So we will talk first about the circuits, then we will talk about the variables, and then about the results. Each circuit contains an input section, a middle section, and an outer section. The input section contains all the possibilities for the source. So you'll have here, for example, 10 possibilities. Each possibility is represented by one I source and one I probe. The user can activate or deactivate any of these circuits. The more circuits you activate, the longer the simulation takes. It increases exponentially. That's why it's highly recommended to simulate one circuit at a time, like one I source and one I probe at a time. The input section has a switch that allows you to select which I source, I probe circuit to activate and which channel to test. If you have many channels, I'm using here, for example, 4 channels. So I'm using a 4-channel switch. If you have more than that, you have the 8-channel option here. So you replace it with, instead of using the 4-channel one, you use the 8-channel one. If you have a circuit or S parameters of 8 channels. The output section, which is this one, is the reverse. It also has a switch so that you can select between channels and the different source and probes. Each eye probe is connected to one source. The number of eye probes must match the number of eye source. So each one of these is a circuit by itself. So I have 10 eye source, 10 eye probes. It means I have 10 circuits here, totally independent. How to control which channel to use and which circuit? We use the global variables list. Again, we go back to the global list. If I click here, I have two numbers you need to watch for. The channel number from 1 to 4 if I have 4 channels, or 1 to 8 if I'm using 8 channels. And these circuits depends on which set you are looking at. If I'm looking at what we call the preset test, then it will be the preset case. If I'm looking at the equalization circuit, then it will be the equalization case. It will decide which circuit you're going to activate or which circuit will be used. Then you have to deactivate the other ones. Otherwise, the circuit will take forever to solve. Now we come to the middle section. It is the S parameter files, but it's more complicated than this. Click on it and push down again. It's a sub-circuit. And this is what you're gonna see. This is your S parameter file from your simulation or from your measurement. And these are additional losses that you need to add at the input and at the output of the S parameter. Why do we need to add more losses before and after? Because of the standards. So this is a picture that we captured from the PCIe SIG Society. And this is, for example, for PCIe 5. There are constraints on the maximum loss of the add-in card and how much is the maximum of the die on package loss, including the die. Same thing for the motherboard, system board. There's a maximum allowed losses, 26.5. And also there are constraints on how much of that is given to the die on package loss. How do we use this information? Depends on what you are testing. Are you designing a motherboard or designing an add-in card? Are you testing RX lines or TX lines? For example, in this video, let's talk about motherboard RX lines. So in this case, I need to add the 9.5 dB at the input representing the add-in card. And I need to add 8.5 dB at the output to represent the die to package loss. This full link should satisfy the specifications. And you will find these information and all these data and all these numbers for all the standards already embedded for you in the template. We go back to the global variables and they are here. Attenuation input even, attenuation input odd, and attenuation output even, and attenuation output odd. So you have to enter these numbers for the input and for the output, depends on what you are doing. You can set them to any value you want. You can set them to the values specified in this table. You see in this table provides you all the information about the values as per the specification for that standard. And you will find similar thing, as I said, for all the other circuits and all other standards. Or you can keep them 0. Maybe you just want to test your bare PCB alone. Now we click pop-up to go back to our circuit. So this is a full description of what you're going to see in each one of these circuits. The circuit, pictures, components, and information. Now we would like to talk about the results. So the first thing to open is the single one. So the single one has only one circuit. So you have 4 channels, and this is where we hide our S parameters and the attenuation lines. And these are switches. These are 4 channel switches. If you are looking for 8 channels, you will find them here. 1 for the input, 1 for the output. So the single channel circuit can be used to do many initial testing. I can also use the optometric to study the effect of the voltage. And as you can see here, this is where we hide the information about the range allowed as per the specification. So for example, for PCIe 3, you are allowed between 800 millivolt to 1200 millivolt. Or you can study the effect of the gain of the CTLE. Again, we're going to talk more about the CTLE later on. So you can run these two, or you can run one case and change things and modify things. So what kind of results you're going to get? These are standard results. You're going to find them in each circuit. So the first one is the width spec. It is simply a bathtub plot, and we use it to calculate the width of the eye and compare it against specification. The user finds the limit line, you see it here, the spec, the results, some instruction on how to reconstruct a similar plot, and finally the Y marker. The Y marker is fixed at 1e-12 bit error rate, as per the spec of the PCIe 3. There is no direct way to calculate the delta of the Y marker, so we are using a small trick in the circuit tool to generate the curve you see on top here. That's why you see instruction says, don't delete this curve. And from this curve, we derive the delta that you see here, which is 0.911. And we compare this number versus the spec. It has to be higher than 0.3. And this is unit interval. The same spec, the 0.3 and the 1e-12 are represented by this limit line. But here you get the numbers, the accurate numbers, instead of just a graph. The second plot is the height. So the eye height plot is simply a contour plot. It's like painting of the bit error value. Again, you will find instructions on constructing a similar one. You will find a delta marker, you see here between M1 and M2, that you need to move manually, unfortunately, because this is a contour plot. This is not a graph plot. It's like painting, as I said. So we forced this plot to have only one contour, and this contour must be at 1e-12 bit error rate. By reading the delta, we get the delta Y, that's the height of the die, and that's the one that we can compare versus the specification, 25 millivolt. That's the spec of the PCIe 3. Of course, PCIe 3, like 4 and 5, they use NRZ signals, and consequently, they have only one eye. For PCIe 6 and 7, we have 3 eyes because they use PAM4, and the spec there is on the top eye, and everything is set for you there. The third graph is the statistical eye report, which is with respect to the unit interval from 0 to 1. If you right-click and you ask for trace characteristic, add all eye measurements, you will get this table with all the information about the height, the location, the average of the 0, average of 1, eye amplitude, eye height, signal to noise ratio, jitter, all kinds of jitter, and minimum eye width and minimum eye height. Unfortunately, none of these can be used against any of the specifications. And the fourth type is the eye diagram, but this time with respect to the timeline, not with respect to unit interval. Notice that we have the mask in the middle, which specify the width and the height as per the spec. Again, here we have a delta marker. If you want to see the delta between any 2 points on the eye, you can right-click and ask to see all eye measurements. And all these numbers are given in time in picoseconds instead of unit interval. I didn't get the chance to talk to you about these different solvers that we have here. So the quick eye analysis is used to generate these kinds of graphs, the eye graphs. The verify eye analysis is used to generate the bathtub graphs. Sometimes you get weird results and you would like to know why are you getting weird results. In this case, use the transient. When you use the transient, you will be able to see the pattern in a nice way. Then you will be able to determine what is wrong with your eye. And we look at the eye at this point, at the output here, using this voltage probe right at this point. The next one is the return loss, where it's an S parameter solver where you bring your own S parameter plus transmission lines before and after, and you try to understand or study the return loss of the whole link. If you do that, you can run also the optometric to run for all the different channels. So this optometric is for the channel from 1 to 4. And if you do that, you get the results. These are the results. And you see here the spec. And these are the values for the different channels for the input and the output return loss for the differential. So there is a spec on the differential return loss. There's also another spec for the common mode. Again, we have all these channels, the output and the input for all the channels. And we have a spec on that, spec at the bottom. And as you can see, we are violating the spec at low frequencies. In addition to the return loss, we have the insertion one, which is similar to the return loss, with minor difference is that if you click on this box and you say push down, you will notice that we are not using the global variables, we are using local variables. By default, they are equal to the global ones, but you can modify them. So this circuit, the insertion one, is to study the insertion, and you will get a graph similar to the return loss with the spec. So we have a spec. We have a spec on the add-in card, which is the first one on top, and we have a spec on the full link. And the information is provided to you here. And as you can see, we're passing the spec. So if I go back to the circuit, I go back, push down, I can modify the attenuation of the input and the attenuation of the output without changing any other circuit in the standard, without changing the other ones. And this is important because I want to use this circuit to study different losses. What happens if I increase the loss? What happens if I reduce the loss? And next, we have the crosstalk circuits. So we have the bare crosstalk alone, crosstalk plus jitter, and also we have crosstalk plus jitter plus noise. So if I open the crosstalk one, you will see that we have 3 sources needs to be activated together to study the crosstalk. And we have 4 channels. So we switch between channels. This is what this switch will do for you. And same thing at the output. And it allows us to study the crosstalk for channel 2 and channel 3. If you select channel 1, this one will be deactivated automatically. If you select channel 4, this one will be deactivated because there is nothing after channel 4. So this is what you're gonna find. You're gonna find that we have added the jitter values, and these values are added to the source, to the middle one, to the source in the middle, under clock jitter. Do not try to change them because they follow the standard. That's why it has its own circuit. And if you go to the jitter plus noise, you will find that we have added the jitter plus the noise together to see the effect. Going back to the preset one. So what is the preset one? So in any PCIe, you can have some equalization. This equalization is done by adding FFE to the I source. FFE stands for feed forward equalization. In the Ansys circuit tool, you can leave them unspecified. Calculate by selecting calculate. And the circuit will optimize them for you. But according to the specifications of the PCIe 3, they have to follow one of 10 possibilities. To study all the possibilities, we use 10 I sources. We have 10 of them. Each one of them has a specific values. For example, this one, these are the values. Because we want to study them all. We want to see which one of them is the best option for this kind of PCB that we are designing. And these ways you can find them here for all the different possibilities for each standard. So these are the values that we are allowed to use for PCIe 3. And all these 10 possibilities are embedded in these I sources. In addition to FFE, we have DFE and CTLE. So if I go to the I probe, you will find DFE. It has a specific number of tabs. Per the specifications of PCIe 3, we are only allowed to have 1 tab. You can leave it as calculated. There are no specified values, so you can leave it as 1 to be calculated by the circuit. So that's why you need to connect it to one source so they communicate with each other until this value is optimized. DFE stands for Decision Feedback Equalizer. The FFE and the DFE are mainly used to compensate for the memory of the channel. The memory is there because of the intersymbol interference and the poor transitions in the PCB. And the last thing is the CTLE. So CTLE stands for Continuous Time Linear Equalizer. It's just a driver with a peak at high frequencies to compensate for the loss in the circuit. The CTLE gain is a variable and can be changed from the local variable list. The range of values allowed as per the specifications is found in the single channel. You will find the range allowed as per the specifications. The CTLE usually have so many poles and so many zeros, and this is the ADC. And some of these numbers here are function of the poles, and some of the poles are function of the zeros and function of the ADC. And all of these are programmed for you, for the user, in each one of these standards, from PCIe 3 to PCIe 7. PCIe 1 and 2, they do not have any equalization. And the last circuit in our list is the equalization. So the equalization allows you to study the contribution of each one of these equalizers. Practically, the user would like to know if he can get away with some of them. Can we get good response using only FFE, DFE, FFE alone, none of them, DFE alone, CTLE alone, CTLE and DFE only, no need for FFE? That's the purpose of these circuits. And again, there is a switch, and you can switch between the circuits, activate them one at a time, run them, look at the results, and make a decision whether this is a good option or bad option. In addition to the main circuits, you also have supportive circuits like this one, where the user can study the interpair skew between two lanes. If you want to study the skew between P and N, you can use this circuit. You can also use this circuit using traditional approach, TDR, to do TDR using the TDR probe. And the last one, use also TDR to allow you to debug crosstalk. The template does not do any design or optimization, but can ensure that the design is meeting the specifications, and by how much margin. As we said before, this template contains all the necessary blocks with the necessary setup so the user can build other circuits to design or verify or test other numbers or other specifications. So keep watching for updates on this template. Thank you.